So in this lecture, we're going to look at methods for evaluating integrals that are what we call improper integrals of type 2. These are integrals where the integrand becomes infinite at some place on the range that we're integrating it over. Right? So what we're going to do is we're going to break this up into three types. Right? The first one, this discontinuity, the point where it goes to infinity, is the left endpoint. And the second one, the discontinuity where it goes off to infinity, will be the right endpoint. And the third case will be the one where that discontinuity is somewhere in between the starting point and the end point of the range we're integrating over. So the way we're going to do this really is very similar to the way we handled type 1 integrals. Right? We're going to rewrite these integrals as limits, or we're going to take the limit as a variable approaches that discontinuity point. Right? So you can see how we handled that here with the left-hand case. Right? This is the point where the function has an infinite discontinuity, and all we do is we replace that number with a variable, a real valued variable, so we can substitute that into the antiderivative, whatever it comes out to be. Then we'll take the limit as that variable goes to the discontinuous point from the right, right? Because remember that point is the left-hand interval. So our function looks something like this, say, and we're integrating from 0 over to this point, whatever it is. Let's call it, put a number in there, we'll call it 1. Right? So we're going to take the limit. So the left-hand endpoint is where the discontinuity is. So we're going to take the limit as our variable approaches that point from the right, because that way we're staying inside the range that we're trying to integrate over. And we'll just do the reverse. Down here with the right hand, where the discontinuity is at the right-hand endpoint, we'll replace the right-hand endpoint with a variable. And again, this time we're taking the limit as c approaches that number from the left-hand side. That way we're staying inside the range that we're integrating over. And finally, if the discontinuity is somewhere in the middle, then we just split the integral up into two parts at that point. Right? So we'll integrate from the left endpoint up to the discontinuity, and then from the discontinuity up to the right endpoint, and then we'll treat the left and right case. Right? We'll do those separately, just like we've done with types 1 and 2 up there. All right, so let's look at an example. We want to integrate this thing from 0, and I've emphasized that we're doing this from the right. The function isn't, we kind of have to, the function isn't defined on the left side of 0, right? Because those values are negative, and you can't take the square root of a negative number. So how are we going to do this? Well, first, I'm going to rewrite this as a limit. I'm going to make this the limit a approaches 0 from the left, right? Because that's inside that interval from 0 to 1, of the integral from a to 1 of x to the negative 1/2 dx. Go put the negative exponent in there, right? Because now it's clear, I think, what the antiderivative is going to be. This will be the limit a approaches 0 from the left of what? 2x to the 1/2. See, I'm doing this way we do integrals, right? I'm taking the derivative of that in my head and making sure we get back to x to the negative 1/2, right? So that's what we need there. And I'm going to integrate this from a to 1. All right, so let's put those bounds in there. This is the limit a approaches 0 from the left of 2 times the square root of 1 minus 2 times the square root of a. And you see now again why it was important to emphasize that we're doing this limit from the left, right? If we were doing it from the right, it wouldn't exist. To the right of 0, you're in negative numbers, and you can't take the square root of a negative number again, so we wouldn't be able to do that. But from the left, we can. This is 2 times the square root of 1. That's 2 minus 2 times 0. Now we get our answer, right? That limit is equal to 2. Okay, so in this case, we have that infinite discontinuity at x equals 1, and that is our right limit of integration. So I'm going to do this similar to the way I did the last one. This is going to become the limit as a approaches 1 from the left of the integral 0 to a of 1 over x minus 1 dx. And I can integrate that, right? This is the limit, still the limit. A approaches 1 from the left of the natural log of the absolute value of x minus 1 from 0 to a. Right, now what happens when I put my numbers in here? This is the limit. A approaches 1 from the left of the natural log absolute value a minus 1 minus the natural log of the absolute value of 0 minus 1. Okay, so this part here, this is the log of 1, which is 0. And what's happening here? Look, the limit is a approaches 1 from the left of the natural log of the absolute value of a minus 1 minus 0. You can go ahead and put that in there. But we're in trouble here. That limit doesn't exist, right? As x approaches 1 from either direction, really, you're going towards the log of 0. And the logarithm is dropping off to negative infinity there. So that's okay. This is going to happen, right? My answer here is going to be that this limit does not exist. And that's going to happen with these improper integrals, right? This method is great for functions where the integral exists, but yeah, I mean, you can see right here, there are going to be times when the integral, in fact, doesn't exist. So this brings us to the end of the exact methods that we're going to talk about for evaluating integrals. You know, we talked about both definite and indefinite as we went along here. We do have one more section to go. We're going to look at situations where you're trying to find a definite integral, but the function that you've been asked to do this with does not have an antiderivative, right? Either you don't know what it is, you can't find it, or sometimes it just simply does not exist. So what do? Because if you're in an engineering situation, you have to have an answer, right? So what we're going to do in that last sequence of lectures, we're going to look at some numerical approximation methods. Because in engineering, you're looking for a numeric answer, and as long as that answer is within your required level of accuracy, it is perfectly suitable. Right? So those are the methods we're going to look at in that section. That'll be the last one in our discussion of integration methods.